Hi everyone, my name is Korea Rudolph. I'm a physician of Iran. I'm currently a postdoctoral research fellow at MayoAI Laboratory and also orthopedic surgery laboratory. Happy to be here with you and talk about diffusion probabilistic models.
Hi, I'm Bardia. I'm a physician also. I work at the Radiology Informatics Lab, the old name, the new name, AI Lab of Mayo Clinic, and also work with the Orthopedic Surgery AI Lab, OSAIL. And glad to be here and be with you today.
Perfect. So, today we are going to talk about a kind of deep learning algorithm which is actually new to us as well. So these kind of models, DPMs in short, are kind of image generation models that have been introduced very recently in the world of engineering and also very recently in the world of medical imaging. And today we are going to talk about how these models can actually be applied to medical imaging, different tasks that we are going to do in medical imaging, and how they might be compared to other generative models that we know, like generative adversarial networks or GANs, and also coders or a couple of other networks that we all might know in this field. So we are going to start talking about what these models really are, how they work, and also talk about some of those applications. And during this presentation, both Patty and I are going to have a dialogue with each other, going to different slides, talk, and also share a little bit of our own experience with these models. So I really hope that you enjoy that we talk and introduce these models to you. I guess that idea we can start and talk about this whenever you're ready.
Just one small notice.
Yep.
This subject is very heavy on math, and we try to simplify it as much as possible. So some of the intuitions that we want to convey might not be 100% correct mathematically, but that's how they work. And we also will share some resources with you that can you can go through to find to get in depth to the math and also the logic behind denoising diffusion probabilistic models. With this introduction, let's get into it. So you might have heard about Dolly. Dolly is a very famous model. Dolly 2 released in, I think, March 2022. And basically what it does, it creates photorealistic images from text prompts. So you might have seen this around the internet, like an astronaut riding a horse in a photorealistic style. So you can give it a prompt and it will give you some images. These images definitely don't exist because astronauts do not ride horses, at least in their astronaut suit. But that's what happens here. And also, you can get different versions of an image. So this is another image with the same prompt. And also, you can have something like this: an astronaut lounging on a tropical resort. So this probably won't happen. And something that definitely will not happen: playing basketball with cats. These are all generated using denoising diffusion model, probabilistic models, which are short form would be DDPMs. And here you can see you can input a text prompt. The model will learn what this text prompt is associated to, even if it had not seen the exact examples, and then give you an image in different styles. So you can say it will be watercolors painting, or it will be a illustration by by a child, or something like that. So this is what Dolly is. And this is the power of diffusion models. So let's get into them. There are several influential papers along the way. The first one was in June 2020, and the concept was, let's say, renewed because it was first introduced in 2015 and renewed in 2020. The other paper, they improve on the previous paper in February 2021, then continued, and they say, okay, we beat GANs, we have better performance than them. Finally, we can have classifiers on them and have the, let's say, noise be clipped and have more precise images. And that's it.
Pardon me, Jonathan, for seconds. So one thing that I really wanted to share here with our audience is that the authors of these papers look to be some sort of people who have really contributed to the science of deep learning. I think you have looked carefully at those papers. Two of the papers had very similar authors, I guess. Dr. Dariwal and Dr. Nikol were actually co-first authors on two of these papers. And in my humble opinion, it's very good to at least respect these authors because they basically, and also people from the brain that basically develop the field. And you nowadays see that most of the papers that talk about DDPMs are actually citing very influential French papers. So just wanted to notify their names and somehow respect them because they're very valuable work they did for us.
Yeah, so it's mainly like the work that we say AlexNet, we say,
Yep.
but this is much recent and it's in
Uh-huh.
late 2020, so
Yep.
that's very close to us.
Yep.
Okay, so in this presentation, we will go over the theoretical basis of DDPMs, how they can be implemented. Will be a pseudocode, don't worry about much coding. And then we will go over the applications and experiments, and finally, what we think about them and what would be the future path for this, at least what we think of it. So let's go to the basis. So there are several kind of generative models. The most famous would be GANs and VAEs you've probably heard about. So GANs, there are two networks competing with each other to create real images. One of them, which would be the generator, gets a random noise or a sample noise called Z, and then it generates an image. And this image will be checked or inspected by the discriminator, and it says if it's real or fake. So this is the basic idea behind GAN. So two networks and competing against each other. The VAEs have two somehow networks. One would be the encoder, one would be the decoder. And we will give the images to the encoder. They will encode them in a latent space called Z. And then if the network is trained well, if when we sample a subsample, when we sample from that space Z, then the decoder will give us a real image. So in the inference time, we will only use a decoder. Similar concepts apply to flow-based model and finally the diffusion-based models. So that's exactly the same. We want to encode our images into latent space Z and then get them back from Z to the original image. That's what's going to happen in this network as well. So when we train the model, we just get a sample of Z and then get them back to an original image, a real image. So the diffusion process has two parts, the forward process, which is denoted by Q, and a reverse process, which is denoted by P. The forward process is essentially creating noisy images based on Markov chain. So don't worry, I didn't know Markov before this, so I will go to that. So basically what happens in the Markov chain is that every step of the way only depends on the previous step. So when you want to create the step of 10, you have to go to step 1, then 2, then 3, up until 10. So we can happen 100 times, 100,000 times, whatever. But the 100th step would only depend on the 99th step, the step before that. So you can here see a radiograph that is noisy, that is clear, and we add nodes to it gradually, and you can see what will happen during the forward process. So you can see that after the end of the forward process, we will be having a very noisy image. You can't see any trace from the original image, and we'll be having basically random noise. So that's what happens in the forward process. In the reverse process, we will gradually denoise this noisy image or noisy vector into a less noisy version. And each time we will try to subtract a little noise from the image. If we do it enough, then we will have a clear image, a realistic image. That's what's going to happen in the diffusion process. Okay, so we say that we want to add noise to our image during T steps, capital T. And this T is usually set to 1000 or even more. But you can see that at the left, there's an image of a dog that's getting noisier and noisier and noisier. And at the right, you can only see noise. You can see no trace of a dog in that image. So this is the forward process. The thing is, if we want to do the forward process, as I said, we need the previous step. So if we want to get the image of the 100 times, we need the image on the step 99. So there's a very good math explanation behind this, but there's a way to approximate what the 100th image would look like without going through all these steps. So if you have an initial image, which is called x0, then you can create noisy version. You can say, okay, this will look like this 100th time on the step 100, and then without going through all the 100 steps. This is a very cool property because you can essentially say, okay, the forward process of the model will be calculated without learning anything, and you have all the variables here. So we say xt is a noisy image at step t. Xt minus 1 is a less noisy image. So when we increase t, we are essentially increasing the noise. And x0 means image without any noise, which means our initial image. And beta t is a variable variance schedule at step t. So this is also given at the beginning of the training. So this is a hyperparameter of the model. It's usually fixed to something between 1e minus 4 to 1e minus 2, something in that ballpark. And then this is known when you start the training. So without needing to go through all the steps, you can have the noisy image at a specific step. So this is very cool and very fast. And this is called the nice property. We will call it the nice property. So having a image at the beginning, x0, you can create xt, which means noisy image at step t, by doing some calculations based on beta and alpha, which is derived by beta as well. So we have beta at the beginning of the training, we derive alpha from it, and alpha hat, and then we can create that image at step t. So this is very easy. This is just some calculations. I don't want to imply that this is very easy to do, but it's doable. Yeah, and it's very convenient.
So Brian, one thing to add is that so far I believe the only thing that we have added to the routine process of training a model is that we have added a set of hyperparameters. Like I mean, right, like beta, like the T, the capital T, which is actually the total number of steps that we are going to make it even more noisy. And basically, we can actually calculate whatever intermediate values that we need based on these new hyperparameters when we first starting the training, right?
Exactly. So before even creating your model, what you do, you can create these images. So we can also add this to your data set or in your data loader, and then go with it during your normal training. Perfect. Okay. And so this is the less math version of that equation. So if you want to get the noisy image at step t, you just have to uh, multiply it by the square root of alpha hat, which can be calculated as the previous slide, and then add a epsilon, and the epsilon would be the noise, which is gotten by torch.randn, and you have a random noise. You add it to your image by different coefficients as described, and you will end up with the noisy image at step t. So you can simulate going through from step 0 to step 10 to step 10, 100 to 10,000, whatever, without going through each individual step. The math behind this, I said, is a bit confusing, but we will provide resources so we can go through and understand it better. But this is the gist of that. And finally, what we want is the reverse diffusion process. So what if we had a model that can say, okay, I'm looking at image step, let's say 102, and I want to denoise it to see what would the image at step 101 would look like. So denoise it a little bit to see what would the previous version look like. That's exactly what we're going to do with the DDPM models. So what happens is that a model will see an image of a dog, a noisy image of a dog, and tries to remove the noise from that image. So there are two ways to do that. One is to see, okay, this is a dog, so the less noisy version of a dog would be something like this. Or you can say, okay, I learn the noise and try to remove the noise. So I say this specific part of noise is extra. I have to remove it in the next step or something like that. This is what will happen in the denoising process of that. The reverse process is exactly the second one. So you can do it with both, but essentially you can say if you guess how much noise was added to that image, then you can say you can use an L2 loss or MSE loss to calculate the difference between the added noise, the real added noise, I mean the one that was we know that was added, and also the model's prediction of what the noise looks like, and subtract them together and get an MSE loss, and then that will be it. The model will learn to minimize its loss based on correctly guessing the amount of noise added to the image, and this will help it learn the overall relationship of the components of the picture, for example, a dog, a cat, a brain, whatever you can put it, and it will learn that.
So, Brandon, before we go to the implementation, what I understand from this reverse process is that we are basically going to move in the reverse direction of the entire steps that we had defined before. So we're basically going to start from the final step, move towards the first step, so basically towards our ground truth image or our first image before it was noisy. And then what we're going to do within each step is that we are going to guess what had been the amount of noise that was added in the first place in the previous image to create the next image. But this time we are standing in the next image and we are going to predict the noise that was added to our previous image so that we can now denoise that noise and move one step back to the previous image. And we continue this process as much as is needed to finally get the ground truth image, right? So this is basically the way that the model is going to learn that.
Exactly. So what we said about T, if T is large enough, we will eventually end up with pure random noise. So if you input random noise, completely random noise, it will try to denoise that, even though we didn't have a meaning for that at the beginning.
Yeah.
But it will try to create a realistic image. You can guide this noise to a way that it will create a astronaut playing golf with you, or you can create and condition it to, let's say, creating a dog or something like that. That's what essentially happens. So when we have 1,000 T's, one way would be creating 1,000 models to, let's say, this model would be for denoising from step one, from step 2 to 1, the other one from 3 to 2, and etc. But the beauty of this method is that they use only one model to denoise all the 1,000 steps. So you input your image, you say what step it belongs to, and then it will denoise it in a way that it will get T-1 step.
Yeah.
And that will be it. So implementation is essentially something like this. The model architecture would be a unit with some, let's say, improvements. One of them would be having more residual blocks, adding QKB attentions after each residual block, adding the time steps. So uh, we also add time steps to each of the blocks, the residual blocks. So each block is aware of what we are trying to denoise and what step we're standing at. And finally, there are some improvements. You can add convex blocks, which are very new, and so many other improvements that can happen. But this is what is different from the normal unit. So you're working with an architecture that has been around for 7 years now, I think, yeah, 2015. And it's doing essentially all our medical segmentations, some sort of in-painting tasks, and it's been used to pre-train some models, etc. So this is known architecture to us, and you can know already that it can be used for many tasks.
So surprisingly, so to my understanding, though, the general architecture is actually the same as the units that you use for semantic segmentation or other tasks based on already familiar units. I mean, the improvements that the original authors actually proposed for these DDPM training is actually quite important and critical. I mean, the core of the value that DDPMs actually can add to the literature is based on many of the aspects that these units have, like those attention layers, as you said, the kind of, or the kind of very interesting skip connections that are between these kind of encoder and decoder blocks. So I believe you yourself have a lot of gameplay, these kind of architectures, and adding or removing residual blocks or attention layers and things like that. So what was your own kind of insight out of these unit models? How important you think these unit is compared to the other components of a DPM training?
Uh, the original unit that mm, they suggest to use, that Darwell and Nickel they suggest, is a very straightforward unit, but with some little nuances. So, for example, Here you can see in our normal units, we have an each block has a skip connection to its corresponding block on the decoder. But here, other than having a group of blocks skipping through the network and going through other side, each residual block does that skip connection. So for example, if in each level, so we call these levels, if in each level you have two residual blocks, the second one will be connected or concatenated to the first one here, and the second one would be concatenated to the second one here. So you can see that there are much more skip connections between these networks. And if you remove them, you will have that checkerboard effect
Yep,
that you know about.
exactly, exactly. I mean, our own units, I mean, the regular units, but whenever you want to generate some sort of images based on, for example, for an in-painting task, you would definitely see those checkerboard effects there. And we were in a period thinking of how we can actually improve the unit in a way that these checkerboard effects go away. And fortunately, the other out of that, it seems that either the sleep connections or the attention are taking care of the checkerboard, which is very cool, very, very cool.
Yeah, and the images you see are very,
Mm-hmm.
very sharp.
Yep.
Okay. So when you want to train this some sort of a model, first, this is the pseudocode from the original paper. It's only 6 lines, but applying that won't be that much hard. So it will be probably 20 lines, but it's fairly easy. So first, you get an image from your data loader without any noise. Then you say, if you remember, we say, for example, we are going to add noise to our image on t equals 1,000 steps. So we select that and the lowercase t, which means the how much random noise you want to add to a specific image, and it will be different for different um, images in your batch. So, for example, if you have a batch of 5, you'll get 5t. So your network will simultaneously be learning how to denoise step 1, step 100, step 432, and something like that. So it's essentially conditioning very closely with the t, which is the how much noise you want to add to this image. The epsilon will be the normal, the a noise that will be added to your image, and it will be a random sample from a random distribution. And finally, here at the second part, if you remember this equation, it's just creating noisy image at step t. And then it will be a forward process, it's calculated, nothing goes through your network. So this is already what you know. And then what we do, we calculate the loss, the MSE loss. There are other variations, but let's stick with the MSE. We calculate the MSE loss between the actual noise, which we calculated at line 4, and what the model thinks the noise was added to the image, the amount of noise was added to the image. So, and that will be your training. So you have everything, you can just run it, you can use your data loaders, you don't need to add anything to that. You can have your images and then create noisy images, calculate, pass them through the network, let the model guess how much noise was added to that, and compare it with the original noise that you added to it. And it will essentially create the mean and variance, if it's going to learn the variance. We will get into that. But it will essentially mean learn the mean of the noise that was added to each specific pixel. So noise is added to each specific pixel. And the output of this would be the mean of the noise that was added to each specific pixel. We won't go into details with that, but know that epsilon is the same shape of your batch times channel times height times width. And during the inference, that will be simple, I guess. So we create xt, which is the image at the noisiest level possible, and we get a sample from the normal distribution, and then we do it backwards. We start from t times 1000, we go to 999, denoise the image, and then finally we will end up with x0, which means the image without any noise, which is what the model thinks the noise represented. Okay,
So Bridget, sorry to jump in. Before going forward, so two questions here for you. The first question is that, so as far as I understand, when you have a batch of data during training, then your data loader actually sends me a batch of data These are different noisy images that the model needs to guess what was the noise added to them of the previous step. But these noisy images that the model sees are not from the same step of noise, right? So, for example, one of them could be from the earlier steps, one of them could be from the later steps, right? I mean, or do they need to necessarily be on the same side?
No, they can be from whatever. So you can sample five numbers from 1 to 1000, and one would be 2, one would be 5, one would be 998, something like that. And
Okay.
the model will learn to denoise these at different steps,
Mhm.
but based on different images. And when you shuffle through your data, you can see it multiple times. It will learn how these steps will work.
Awesome. And then, so another thing that we both noticed when working with these models was that the inference time of these models usually take a lot, right? I mean, take a lot of time, at least much higher than what GANs or autoencoders would take. And I believe one reason for that is that the image, the original noise image that is going to finally be converted to an actual image needs to be denoised multiple rounds, right? So it basically needs a lot of iterations.
Yeah, and you can't batch something that needs to be inconsequential. So
Mhm.
you have to first put a batch with time step 1000, get the results, do it again. So the problem with DDPMs, as I think you will get to,
Mhm.
is their long inference time. The how to shorten this time is an active area of
Yep.
research. There are some ways around that, but still, the best results would be get when you go through all the 1000 steps.
Awesome. Thank you.
Sure. And so you might be thinking about, okay, we have GANs, we can condition them, etc., etc. What can you do with the DDPMs? So there are multiple ways you can condition a DDPM model. First, you can add a separate channel to your noise, to your initial image. And that will be something like doing super resolution, as Puriya will discuss. So you create a low res image, you upsample it using, let's say, linear interpolation, you will get a blurry image, and then you try to condition your noise based on that blurry image. The model will probably learn how to denoise the noise so that it represents a high resolution version of that initial, that separate channel, the conditional channel. The other way would be, let's say, adding classes, class tokens, or let's say class embeddings in form of text to your time step T. So these T's that will be added to each block of the network, they can also carry some class information as well. So there is another way to do that. The third way would be creating another classifier that's trained based on diffusion again, and then use the gradients of that to train the model, the generator model of your diffusion. Something like a GAN, but it won't be, the second model would be a classifier. It won't be a discriminator. It won't tell you real or fake. It will tell you the class probability of that image being related to a certain class. And that's conditioning it. So we have covered how the math behind them, how they work, how would we add noise to an image during forward process, how we denoise that. I mean, we don't denoise that, the network does. And then finally, how we can implement that easily. There are some public implementations of that you can search for. And getting started to work with them is really, really easy. Just import a package and let it let it see your data, and it will start training.
Perfect. Thank you so much. You have been very, definitely very insightful. So now what I'm going to do, and please feel free to jump in and complete my words whenever you felt necessary to. So I'm going to talk about the application and experiments, and I'm going to mainly focus on medical applications of DDPNs. But before we start, I would like to emphasize that these models have been out, I guess, mainly for 1 and 2 years. I mean, there are some initial papers that have been out since 2015 or so, but the most influential papers came out in the recent 1 or 2 years, and they came first in the world of engineering. But there are in the past few months, some papers also came out in the world of medicine, specifically medical imaging. So you can consider most of the applications that we are going to talk about right now proof of concepts paper. Yet they are very powerful papers. I mean, you that those algorithms like GANs or autoencoders have been out for years, and people have been actively researching on them. These DDPMs first examples are going to beat GANs and autoencoders from many aspects. So they do have their own upside, and people are still working on them. And this is only the start of it. I mean, in my own opinion, years of research on DDPMs. So let's just jump in and see how these models are going to be used in the world of imaging, and then we probably can talk about each example. So I'm going to talk about, first of all, unsupervised image generation. It's basically the first kind of application that comes to mind when we talk about any kind of image generation, like GANs or DDPMs. And the first paper that I'm going to talk is actually this paper on diffusion models with GANs and synthesis. I guess this was one of the first papers that Bardia also mentioned from those highly influential papers. So these papers going to talk about that how GANs can be used to generate images like these. Now, look at the quality of these images. These images look very, very realistic, but all of them are actually fake. And as you see, these are somehow quite similar to the kind of images that get out of out of very modern and recent architectures released from the GAN family, the style GAN. So this is how DDPMs can be used for unsupervised image generation. And again, I should emphasize that this is only the first generation of DDPMs. We definitely should wait for the upgraded models to come. But even first generations can create images as realistic as these ones we are seeing here. And of course, that the only example that Bardia talked about in the beginning of this presentation is also a very good example of how unsupervised image generation can happen using DDPMs. Now let's proceed and talk about one of our own experiences. So Bardia, let me ask you again to comment on this because this was one of the first DDPM models that you yourself trained, right? So these images are all physics, am I right?
Yeah, these are all created by by a DDPM. So it's a vanilla DDPM without any class conditioning. So it's all trained it's trained in an unsupervised manner. And you can see the difference of the views that a model creates. So the one on the right, you can see is creating a long view of an X-ray, and on the left, it has put a device on the femur. Uh, we have had experiences with Korea. You can just testify on that on Stargans, and all of them look something like the middle image with some different in intensities, but they fairly looked similar to each other. They were different, definitely, but fairly similar. But this one, you can see that it has learned lots of data, learned a lot from the data distribution and create diverse images. And if you look at the right here, so the first image on the left, you can see that if there's an R marker on the right side of the patient, and you can see also another one on the left side of that image, but it's flipped. This is because we have flipped our data. But the style GAN would have created a straight R because the GAN is learned that an R looks like this, and it might be on either side of the image. It doesn't matter where you look at, but this is the beauty. So these learn the word model much better than GANs, at least to our experience.
Yeah, so you're saying that these models, DDPM models, are superior to GANs in learning, word model, location, and some sort of abstract concepts like these that usually deep learning models struggle to learn, right?
Yeah, so they will know, okay, this is femur, a long view of a femur. If we had some, I don't have the images here, but if we had knees in our images, we can have knees connected to hips. So in a very anatomic fashion, so they will learn a lot.
Perfect. Yeah. These are really natural things. We do not have too many instances of those images that you have here on the left and right side of the screen. We do not have too many instances of them in our very big repository of pelvis images and diagrams that we have. But you can see that these models are actually creating fake images from these kind of outlier images, very similar to the outlier images we had, which is one of the advantages of DPNs. We definitely capture more diverse distribution of your data. So let's proceed and talk about other things that we see here. So again, I believe these might be a comparison of the two images that you created. One using Steigen and one using Egyptian, right, Nadia?
Yeah, so I don't know if it's visible here, but if you zoom in on the Sagan one, you can see some watercolor effects, some smudging on the bone and on the muscle, but you won't be able to see that artifact on the left side, which is very cool here.
Yeah. So it seems that even the quality side, EDPMs can beat, Steigen 3 at least, which was the model that we were working with, or even the more modern kind of Steigens or other architectures. So that's really cool. All right, so let's talk about the other paper, which again was one of those papers that Bardia mentioned. So this is talking about conditional image generation, which basically means that now you are still going to create some sort of synthetic images in an unsupervised fashion, but this time you are going to force your model to create images from specific classes that you are interested in. So, for example, when you look at images here, you will see that on the right side of the screen, you are seeing images that all from the husky class, from one specific class of the dog. Whereas on the left side of the screen, you are seeing the same model producing images in an unconditional fashion. So this means that when using DDPMs, you have this capability to create synthetic images for specific classes. So you could, as Verdio said, condition them on a specific class that you're interested in. So this is super interesting for makeup as well, because when you are creating synthetic images, you might be interested in creating images that showing a specific pathologies or maybe a kind of a specific normal variant of location population. So this means that these models have the potential to do something.
So one question for you, Adam.
Yep.
So in GANs, you can say if you want to get less diverse images but higher fidelity
Mhm.
images, we can say, okay, we truncate the normal distribution that we give to the model as
Yep.
noise input,
Yep.
and we get fairly similar images, but we know these are high fidelity.
Yep.
These would
Yep.
definitely be good, and we can use them whatever use case we have.
Yep.
So is there a possibility here?
Yeah, so basically, so there are two ways that have been explored so far for making these EDPM models conditioned. One is, and which was, I believe, one of the first approaches tried, actually use an external classifier that penalizing the model during the training and forcing it to create a specific classes. But I believe the paper that we just showed to our audience here, that was a kind of classifier-free type of DDPM. So the term classifier-free means that there is no external classifier forcing the model to do something. And the only trick here is that we are mimicking something like that truncating behavior you mentioned before, so that we are actually asking our DDPM model to give us a specific part distribution that it can generate. Yes, as far as the distribution, the main distribution that DDPMs create are much more diverse than the distribution of the GAN. Even a truncated version of that distribution is going to show much more diversity compared to a GAN. I think this is what all I understand here. These huskies have, although they look all the same from sort of the kind of dog in them, they have different properties from the background scene and also the type of the face expression of the dog and things like that. So this is not something that you could easily get out of again using the truncation trait. All right, so let's proceed and talk about other models that we have. Now, I'm going to now moving towards more kind of medical theories that we find in the literature so far. So first, let's talk about a very clear application in medical imaging that most of the people active in deep learning on medical imaging data have probably encountered before, and that is semantic segmentation. Basically, paints different structures that you're interested in using a deep learning model in your input data. It seems that fusion models can do this thing in a very interesting way, and that way is actually label efficient. So as you see here on the title of this paper, you basically can train semantic segmentation model with very few labels. And let's move to the next slide, how this is possible. So earlier, you had a very recent experience with this label efficient kind of architecture. Do you want to explain it yourself?
Yeah. So what happens here is you create a diffusion model that creates unsupervised images for you, and you basically with noise, you denoise it 1,000 times, and you will get to a hip image, for example, in our case, and then that's trained. You have it. You don't need to train it again. You only, for example, have a hip, a pelvis radiograph, and then you will pass it through the network in certain steps, and then you extract the features from the bottom layers and also the intermediate blocks of that unit, and then concatenate them to each other, and then classify based on those features. So what we did was fairly similar to this paper with some key differences, but we had the features concatenate to each other. Here they use a pixel-wise classifier with some linear layers. We use a very small unit with 2 million parameters, which is very small in terms of units. And then we had, let's say, the dice score for the few-shot learning model, which used only 20 images, was around 90 in some cases or 80. And then for the model that wasn't trained, that was trained using a efficient net backbone of unit, it was a 40 to 50, which is a huge improvement by having fewer number of data.
Perfect. Yeah. So I believe the authors here talked about semantic segmentation, but the kind of concept that we can understand from this paper is much, much deeper than that. So basically what this paper is saying and what these experiments and also what Mario just talked about show is that DDPMs are very efficient in learning meaningful semantic features out of our images, which basically makes them very, very valuable candidates for self-supervised learning or even, as Radia said, semi-supervised learning or few-shot learning, because now we understand that the kind of features that the different blocks of these units have learned are so, so valuable and are so meaningful. So basically can transfer learn from maybe the encoder of this unit model and then use that for semantic segmentation as a tier, or maybe for even classification and other kind of routine, tasks that we usually do. So I believe this would be an active area of research upcoming years for DDPM models, and they might somewhat revolutionize the field of transfer learning, at least in medical imaging. We always face this routine problem of scarce data. All right, so talking about the other kind of architectures or applications that we have, so I believe one slide that I just passed is again showing the results of this semantic segmentation model. Here that their model was also trained on 20 images, like how we did our trained our models, and the semantic segmentation maps look quite high quality. I mean, if you just keep this in mind that these models have been trained on 20 images, and the networks that were used for final training had very, very small layers. So this kind of results that you are seeing on the screen is mind blowing. I mean, compared with the kind of data we need and the kind of architectures we need to do a root segmentation task using any kind of unit that we might be working with before.
Yeah, and also if you use it to create synthetic images, all your synthetic images will have that label as well. That's
Yep,
very cool.
perfect. I mean, yeah. So a lot of differences. This paper was also among the very influential books to be read recently, and there are a lot of applications coming out of it. All right, so let's go forward and talk about another very familiar application of DDPM. So most of you might have heard about super resolution and how this is actually useful in medical imaging. So most of the time we are dealing with type of images that are actually low resolution or maybe noisy or based, not in the quality that we are looking for. And then what researchers in the field of deep learning usually do is that they train super resolution models so that they can feed in a low resolution version of an image, say, for example, a 64 by 64 image or maybe 56 by 56 image, and then receive a very high resolution version of the same image as an output, for example, the 24K by 48 or 1024 by 1024. So we used to do super resolution using a lot of architectures out there, saying that we can basically do this in our own lab here at one very nice publication based on super resolution, which was called Sukyan. But it seems that DDPMs have also been explored in these fields. So let's move forward and see the results of a super resolution model trained using DDPM. So on the left side, on the column titled input, you will see some low resolution versions, I mean, the input images to the model, and on the right side, we are seeing the high resolution version of those. And it seems that the model has been very successful in making the images clearer and also, um, you know, denoising them in a way that the final image looks like much, much improved from the terms of quality. So it seems that super resolution is another area of research that we probably can explore in medical imaging because we're dealing with a lot of tasks that uh, needs to be done using super resolution. And moving forward, a very similar kind of application is also called noising, which you probably all know about. So whenever we are working with some sort of noisy MR images and images that are actually full of artifacts that we really want to get rid of, I mean, denoising deep learning models can come into use. And again, this is a field that most of the times have been explored using generative adversarial networks. But again, DDPMs uh, also being tried here in this field, and the results look quite awesome as you see here. So here you will see that there is an input model here, and you see that based on different variation of the denoising model, you can receive an output of the same image that is denoised. And the alpha here is actually a kind of hyperparameter that the original image is, and somehow is configuring the level of denoising that the model is doing. So the take-home message from this paper is that DDPMs can also be used for denoising MR data, as you see here on the screen, and it seems that the output results of these models are also quite comparable to what we see from GANs.
One thing I wanted to add to this paper, this is a very cool paper. What they do is that when you get a fast sequence of MRI, fast MRI, you will have noisier images compared to normal images, I mean slower MRIs. And what happens is that they calculate the time, they simulate what this image looks like when you want to pass it to a diffusion model. So, for example, this image looks like it has the amount of noise of a step 100, and they will pass it through a denoising model 100 times, like what we discussed, and it will denoise that, which is a very cool feature here.
Yeah. I mean, a lot of applications for that. It seems that people have already started to try these models in the world of medicine. So now let's move to another area, or better to say, to another family of applications that we can title all of them as paired image-to-image translation. Now, let's talk about the examples, and it might become clearer what we really mean by paired image-to-image translation. So, the first type of application that you might be familiar with is actually in painting or maybe on cropping. So in painting means that you will have an image, and part of the image is actually cropped, maybe zeroed out using 0 pixels, or just somehow you have cleared a part of the image, and now you want a deep learning model to guess what the removed part is the beginning. You might probably guess that this is a lot of application in natural images and in applications like Photoshop, where you usually use to repair old photographs, for example, but it also has some sort of applications in medicine, and to be honest, one of my own interests in medical imaging. Now, what you see here are examples of non-medical applications of paired image-to-image translation. So, on the left side, you will see the face of a lady that had been, first zeroed out and then filled with random Gaussian noise, and then as the training, progresses, that noise is gradually converted to the real face of the lady. And you see that the final image on the uh, rightmost side of the image is showing a very naturally looking face of a woman that basically might be different than the original kind of face, but it had been built very naturally. So, you cannot easily say that this is a fake image. And this is an application of painting because it's image to image translation. So, you feed in an image that has one part of that masked out using a kind of noise or maybe 0 pixels, and then on as a ground truth, you have the full version of that image, and the model is going to learn how to build the full image, the incomplete image. And on the right side, you see other versions of this paired image-to-image translation. For example, you could convert the black and white or grayscale image to a colorful image, or you could basically complete the other images that here that might be somewhat distorted using some sort of lines, or maybe again cropped out, and then you are going to return back them as the final image. And you can also compare the original image with the output of them. It does look quite realistic here. Okay, so this third image to image translation has been mostly explored in non-medical fields, but we ourselves have also tried versions of that using in-paint models, and how we could actually do that on our own kind of medical imaging data, and the results have been so far very good.
Yeah, so I know Pri, you worked with the units to
Yeah.
do the painting. You
Mhm.
also, I mean, vanilla unit, and then you also use with the DDPM. So
Yep.
what would be different that you mainly saw there?
So yeah, so that's very interesting because, so as I said, our first experiments were in painting on medical imaging data, which, as you know, we usually work with radiographs and deep radiographs. And uh, using unit to do an in painting on those radiographs resulted in very good looking images. But when you zoomed in on those images, you could have seen artifacts like checkerboard effects mentioned. And it seems that, so we knew somehow that these effects were there because of the kind of architecture that we use, and the kind of maybe few skip connections that were present between the encoder and decoder parts of the model. But when we change the training toward a DDP type of inpainting, those checkerboard artifacts went away in very first step of the. This could be due to improvements in the unit model itself, and it could also be due to kind of different style of training that these DDPMs follow. And either of that is true, the kind of images that I'm getting out of my DDPM model is actually quite superior to the kind of images that are received from the unit model. And it seems that, again, as we saw in other experiments, the variation of the images, or the variation of uh, you uh, completeness that these DDPM models add to the original masked out image is actually much more diverse compared to the kind of images that you got out of it. So basically, the DDPM model is able to complete the image in much more diverse ways compared to a deterministic unit model that is always complete the image in the same page. All right, so let's talk about unpaired image-to-image translation. Now, some of you might have heard the term cycle again. So most of the time, at least in the medical field, we do have images. Different type of sequences or different type of scans from the same patient. So for example, imagine you have a patient with an MRT1 scan, and you also have a T2 scan of the same patient, most of the time captured at the same time. And you might be interested to guess the T2 sequence from the T1 sequence. So that's called a paired image translation because you have those images from the same subject at the same time. But there are instances in which you do not have paired images for your study population. So a very famous example of that, which was basically introduced in that Cyclegan paper back in 2015, is how you are going to convert images of horses to images of zebras or vice versa, because you definitely do not have a zebra that is standing in a photo quite at the same, similar to a horse in another photo. So you basically have many photos from horses and many photos from zebras, but they are not one-to-one images. So in 2015, researchers actually thought of a very interesting architecture that could convert images of zebras to horses or vice versa, these kind of paired image-to-image data sets. And it seems that the same task could also be done using DDPMs. Now, the kind of thinking behind this and how the authors of this paper actually related two different DDPM models to each other is very interesting. I'm not going to talk about the details here, but the final example is going to be something like this that you're going to watch on your screen. So you see here that, different models that have been used for unpaired image translation have been compared with each other here. You see the famous cycle again on the second column from the left, and you also see the result of the other work on the right column that you see on the screen. So again, you might see on the screen and see that, all right, so these images, so that the goal here is to convert images from one slide, from one kind of style to another style. And you might see that, all right, so these images do not look perfect, but remember, unpaired image-to-image translation task is very difficult to have because you do not have a paired ground truth. And when the cycle game paper came out, it was very revolutionary because nobody thought that different models would be able to do it. But now not only cycle GAN models can do that, it seems that other kinds of architectures, and very recently DDPMs can also do that. And I believe this is a very active field of research, and people can really improve the results here based on DDPMs because this model learn features much wiser compared to the GAN versions of this kind of task. So I believe it's a field that we will see a lot of improvements in. And then moving forward, so this is another interesting application here. So lesion manipulation, or in other words, adding or removing lesions to images in synthetic ways. You might say, how this is possible and what I really mean by that. So let's jump into the examples here. So what you see here on top is actually the kind of normal lesion scans here, brain scans here. And in the bottom row, you see that some lesions have been added to the same scan. And it seems that these lesions at least were homogenized, not fake. These look like to be coming from real patients. And the kind of architecture behind doing this trick and adding synthetic lesions to realistic images is again DDPM. So what researchers did in this paper was that they worked for some sort of image-to-image DDPM models that could introduce lesions to kind of unseen, or to kind of imaging data that didn't have those lesions in the first place. And they also, I'm not sure if I have this slide here. Yes, so they also worked on different type of tasks here. So for example, they could change the lesion size, make it smaller or larger. So you see here that again on the top bottom, on the top row here, as the input, you are looking at some lesions, and those lesions have grown in the bottom row, which is actually the output of the model. So they picked the lesion, they made it bigger, and they actually generated a realistic output image for themselves. So this is how the magic is happening using DPMs. You could basically play with any lesion in real imaging of some patients. You can add lesions, remove lesions, or change their size, which is very interesting.
One question for you on your previous slide.
Yep.
So, did you?
Oh, sorry. We should move on.
Yeah.
Okay.
So, is that star really what they included in?
Yeah, it is. So it's really cool. Just imagine. In my own opinion, they were just playing with this model. So they just built a mask in the form of a star on the brain, and they said, okay, let's see if the DDPM model can generate a realistic lesion somehow similar to the star. And it turned out that it could. We look at the real lesion there. I mean, it's not definitely mimicking the entire format of the star, but it's probably the most realistic version of the lesion that could be similar to a star, like what the authors put there. So yeah, it's again proving how powerful these models are. You could basically put any kind of mask with whatever arbitrary shape you're interested in, and the model take care of that. It will actually a lesion like that to your real image, which is very yeah. So with that said, let's jump into the final thoughts that we are going to talk about this model. So before I proceed, so right, do you have anything to add regarding this test? All right, perfect. So let's go and try to stop our talk here. All right. So I mean, we actually mentioned sorts of generative models here in our talk. I mean, we talked about GANs, generative adversarial networks, which probably are the most famous type of generative models. But some of you might have known or heard the term autoencoders, or maybe even heard the term normalizing flow models. So these kind of models so these have been in the literature for years, and we know that GANs are known for the high quality samples they create, and also the fast sampling, which means fast inference. So you could create thousands or 10,000s of images with GANs in few minutes. And now talking about autoencoders, they are as fast as GANs are, but they cannot create as high quality images as GANs can. But at the same time, they even actually cover more diversity, basically cover a more diverse range of input data that they create or output. This is something that GANs cannot do. So earlier I kind of mentioned before that when we get images out of GANs, they mostly are similar to each other. I mean, yes, they are different, but they are definitely going to capture whatever differences they saw in the training data. But this is something that autoencoders can do. Now, talking about DDPMs as something new that is recently added to the literature, that DDPMs are good in creating both high quality samples and at the same time creating very, very diverse type of samples or synthetic images. But what is their downside? The downside, as Radia mentioned before, is that they are really slow during inference. And the reason is that you are going to denoise an image multiple times, even 1,000 times, during an inference to receive to get that original image you're looking for back. And this might still be fast on GPUs, but these models are not going to be definitely as handy as generative adversarial networks or autoencoders are. They needed to be run on some sort of fast applications like on the fly prediction like that.
Yeah, so for example, the Sagan would create 50,000 images
Mhm.
in 3 minutes. But if you create 50,000 images on a using a, let's say, DDPM model in a smaller size, 256 by 256, it would probably take 5 to 6 hours,
Wow. Yeah.
which is very long. And as I said, there is this area is an active area of research to make them faster, but there is much to be done.
Yeah, I mean, we are still beginning playing with these models. Let's even right now there are some papers all talking about different approaches to make inference faster. But anyway, we should acknowledge that these models don't have this downside. Though in many applications that people might not, consider fast inference as a kind of critical feature of their algorithms, then again these systems are going to be as good as GANs and autoencoders in different areas. So basically, we should rely on those cases. All right, so let's move to the next slide, which is basically talking about the main pros of diffusion models. Now, we basically covered most of this before. So we said that these diffusion models with DDPMs can create high diversity and at the same time high fidelity synthetic images, at least compared to GANs. Their training is actually much, much more stable than GANs. I remember that you had experience training with GANs, right? And I remember that you somehow were really very curious regarding how GAN training sometimes move out of stability and you need to restart your training, right?
Yeah, and also there are some ways to stable them, like extracting GANs, sorry. But I think they're very unstable. You need there is a very narrow range of hyperparameters that will work best.
Mhm.
And but for DDPMs, you can throw it like very normal training. You might not get optimal results, but they're very acceptable as opposed to GANs that might they will generate nothing. they
Yeah.
would easily have more collapse, which is not the case with the DDPMs.
Yeah, I mean that's a huge benefit. I mean, multiple aspects, universities and all want to escape this, but unfortunately, this is not the case with the DPM models. All right, so the third one here is that DDPMs are very flexible, and the reason is that the main architecture that these models are going to train is actually units, and units have been out there for years, and people know how to work with it. Everybody knows what an encoder and a decoder are, and how to play with them, how to add skip connections, how to add residual blocks, or even add interlinks. So, and another important thing is that you could basically add whatever additional data that you're interested in to this model, so you basically can add many other type of variables, maybe clinical variables, or even other type of image data that you're interested in. Either you should one of these guys as either additional channels to your input data, or maybe some sort of added layers, added values to those bottleneck layers. So actually, there are a lot of ways that you could play with this diffusion model. So the architecture looks very flexible, and this, in my humble opinion, is going to make a lot of applications possible for these models. And then easier conditioning is again something related to the previous point. When you have a very flexible architecture, you can condition that on many different things. And they have a pretty straightforward implementation. I mean, yes, of course, the math behind that is complicated, but I mean, so you do not need to understand all details of the math in order to work with these system models. So you just need to understand to have a general intuition of how these models work. And when you do, then there are packages out there that you could implement, or even if you want to code everything from scratch by yourself as we did here, this is not going to take too much of your time. 1 or 2 weeks of active working and coding, and then you will have a working model. Unfortunately, the pioneer papers that came out mentioned a lot of hyperparameters, a lot of coding details that you could rely on, and then develop models here. And finally, this one thing that again is one of my own personal interest here with DDPM models is that they are very useful for uncertainty quantification. So this term is itself a new field, or better to say, a recent area of research in deep learning, where we want our deep learning models to tell us how uncertain or certain they are when they make predictions. And this is something that I believe it should be mentioned, should be more emphasized, at least in medical literature, because we really care about how certain our models predictions are, because it is related to the patient outcomes, and we really want to make decisions based on models outputs whenever they are certain. And now, talking about DDPMs, I mean, you can actually, I mean, because these models are based on sampling, and what they create is somehow mean and standard deviation. So you have measures, you have mathematical measures to understand how certain these models are, and you probably can use an innate property of these models, which is those distributions, to understand how how wide or narrow a predicted distribution by a model is. So, for example, if you feed in an image of a patient, you want to convert it to another image, maybe of another sequence or another scan, and you see that your final image is coming out of a distribution with a very, very high standard deviation and a very wide distribution, you might somehow doubt that it seems that the model was not quite sure how to generate this final image. It seems that the image is coming from a very wide distribution, and a lot of instances of this image could have been created. So the model like that has been restricted. So again, to cut myself short, uncertain quantification is something very new to the field of deep learning as a bit for the whole video, but uh, DDPM models can be useful in this field, in my own opinion, in very, very efficient ways. And then finally, let's also talk a little bit about the clones of these models. And the clones, so the main clone, as we mentioned a couple of times, low inference speed, but there are a lot of, I mean, there are a few other clones as well. So the sophisticated mathematical theory, which in my opinion, and Brady's opinion, could also be an opportunity for those who might be interested, because it could probably take some time for other people from the medical field to get active in this field. Even in the engineering field, some people actually, I mean, prefer not to with these kind of models that have a very complicated math behind them, but I mean, then they are easy to implement. And well, I mean, but the other thing is that these the kind of unit that these models are trained with, they are very larger than the kind of unit that used to work with before for routine semantic segmentation. So Maria, let me begin here. So you have a lot of experience with these different unit models. How big this unit, at least the original unit that Gary Wall actually put in the paper is when training your models? I mean, how much you compute to train those models?
So the network that proposed for creating 256 by 256 images is around 130 million parameters, which is very large compared to the units that we use, 30, 40 million parameters. And also, other than having a lot of parameters, the problem is with the efficiency. So when they have so many channels, so many attentions, they use a lot of memory that is not proportional to the number of parameters that they have, and it will make training slower. It's more stable, but it's very slow compared to the, we say, okay, I have a 130 million parameter model. I have trained before with a back size, let's say 128, which is what we did. Yep. But here we can only try on batch sizes around 30 to 40 on an A100, which is very slow and very inefficient. There are some other alternatives, but to the best of our knowledge and our experience, the original unit also works better than the other alternatives.
I mean, the side of the story is that fortunately, the companies like NVR, I mean, they are operating their GPU cards over here, and at least, referring to MayoAILab, we should expect higher capacity features coming out every year. So hopefully, this will not be a very huge problem in the future. But again, yeah, I mean, at least at the moment, these models are actually heavier than the previous models that we used to work with. And the final thing here is that this is a natural device. I mean, diffusion models have been out in the picture for about 1 year or two, and GANs or the other competitors in the field of image generation have been there for 5 or 6 years. I mean, Nove in the first 2 years of the GAN introduction, papers came out with the title like the StyGAN. I mean, StyGAN came out years after active research in the field of GANs, and where GANs were the only candidates for image generation of high-quality image generation. So we currently can see that diffusion models can even beat architectures like StyGAN in many kind of applications. We should bear in mind that these models have been out only for 1 or 2 years. So probably in an upcoming decade, we might see much more kind of applications of diffusion models. So that's something quite natural here. And now let's talk about, I'm going to show you as our final slides here, some sort of benchmark. So this is a benchmark of image generation models on ImageNet 512 by 512 images. So basically, this is an unsupervised task for creating images similar to what we have on ImageNet, right? And the task is to create 512 by 512 images. And this kind of ranking that you see here shows that first, the most powerful model is the StyGAN X large. And after that, whatever you see, I mean, the other two rows are actually diffusion models, DDPM models, different variants of that. And now, the first one here, that as you see, DDPMs are standing among the top ranked competitors. So though they are very new, they do have one of those, I mean, very top rows here. I'm saying that they are very ranked very high compared to the other competitors that are out. But you might ask us, so if something like a StyleGAN X large still holds the first place, then what is the point of talking about these skills and things like that? Because even though they are new and they are interesting, they cannot still beat a specific kind of StyleGAN that is called a X large. But so that basically that was a question for us. And then we went and studied about large, see what that model is actually doing and how it looks like in terms of architecture. And to be honest, the architecture is something similar to what you're seeing here on the screen. I'm not going to jump into details here, but let me just very briefly tell you that the StyleGAN X large is based on one generator and 9 discriminator models. So 8 of them you're seeing here plus another discriminator. So 8 or 9 discriminator and then one generator. So about 10 different architectures being trained at the same time compared to one single unit that the DDPM models have. So yes, I mean if you can train 10 different architectures at the same time, and if you can also deal with all the stability issues that Barry talked about, yes, you basically can beat DDPMs or probably whatever other architectures that you want to train as a competitor. But the goal, I mean, the main point about DDPM is that they are flexible, they are only based on a single unit model, and yet they have stood actually in one of the top ranks compared to other type of plans. And yes, I mean, something like a Snug X large probably can beat them, but I'm pretty much sure in future, I mean, DDPs can also beat the Snug X large very easily. So that was, I mean, I believe, most of the things that we wanted to talk about. As the final slide here, let's also talk a little bit about areas to explore. So As you mentioned, comparing the performance of DDPMs versus scans is an active area of research. Investigating the efficient hyperparameter for training diffusion models because what we are using right now is actually based on those few papers that have been out. But I believe there are a lot of other ranges of hyperparameters that we can try for different tasks. I mean, different unit-like architectures. I mean, so Paddy already did a lot of work and experiments on that. I mean, he tried different unit architectures. Currently, I believe, as you said, the original unit is actually doing a very nice job. But I'm pretty much sure that sooner or later other kinds of architectures are actually going to be used and implemented them in different applications. Conditioning approaches and also relying on diffusion models as feature extractors are other areas of research that people can work on. And finally, the YouTube quantification, as you mentioned, is also an area of research. Now, I believe this is our last slide here, Brandia. So do you have anything to add or to wrap up our conversation here and then we can say farewell to our audience?
No, thank you very much. So it was a pleasure talking to you, Korea.
Well,
And we learned a lot about DTPMs. We'll definitely gonna learn more about them in the future. And I just wanted to see if you want to learn more about DTPMs or other areas of deep learning, go to Little website, and there you can find resources from notebooks, codes, and also texts about different from start how to start a deep learning project in medical imaging till more advanced topics from to like unsupervised learning, DDPMs, uncertainty quantification, etc. And thank you very much.
yeah, thank you very much. And also, I would like to thank our mentors, like Brad Erickson, who actually taught us a lot during the past few years. And I'm very much happy and fortunate that we had the chance to go through these all new fields under his kind mentorship and supervision. And also, all other colleagues that we have here in the lab, who actually have created a very productive environment for the two of us. And I should also share idea because two of us together had a lot of experience with these new models, and it's really fun. I mean, the main reason that we put together this presentation is that DDPMs look mind blowing, very interesting to us ourselves, and then we wanted to share what we're excited about to you as well, and let us know if you're interested in this topic, want us to go to other tools and also the middle website itself. And I believe that's it. Let's farewell to you and hope that we can see you in other presentations as well. Thank you very much for your attention. Goodbye.
Thank you. Bye.